Hey, good afternoon, everyone. So I am preempting all the SCEDEX talk for the day with a fair scheduler talk, and I myself will get preempted later by a deadline scheduler talk. So hi, I'm Prateek. I work at AMD, and today I'll be talking about the Linux load balancer and some of the concerns that have been reported in the community in the past and how we are trying to tackle them one by one, and would like your input to know if you are going in the right direction. So, what is the actual motivation? So, last year, Chen Yu posted, no, 2 years back, Chen Yu posted this patch where he mentioned that on the Sapphire Rapid server, they see this a lot of cycles being burned by new idle balance. And out of the new idle balance, mostly it is the update HDLB stats. So, mostly the stats accounting is taking a long time. And this was also backed up by Matt Fleming from Cloudflare, where he publicly reported that this is something they see on their production servers. And it is not very uncommon because people don't tend to overload their servers a lot because they have to maintain SLA guarantees. And in order to maintain those SLA guarantees, there is a little bit of headroom that always exists. And CPUs do tend to go in and out of idle very frequently because the headroom is not a lot, but the utilization, there is that room of utilization uh, which the deployments leave, and because for that we see this phenomenon. And load balancing is often done in a non-preemptible context. For new idle balance, it's done in the select task RQ fair when going to idle, and for the periodic balancing, it's done in the soft RQ context. So we would like to minimize this as much as possible. And some of the optimization that have been proposed in the past around new idle balance include Chen Yu's ILB util, which limited the number of groups you had to scan in a very busy system. The rationale there was, in a very busy system, if you scan, say, one group, you may already be at the busiest group. But in our testing, that didn't turn out to be true all the time. David Vernet's shared Runqueue was another thing where he wanted to reduce the cost of finding a task to pull towards an idle CPU. But the latest version had some problems and we couldn't get that working in time. So we generally decided to tackle the update HDLB stats problem. But before going there, let's see whether does it even matter. What if we just rip out new idle balance from the kernel? What actually happens? And does it even make sense to go and optimize all of these bits? And what we saw was there's a bunch of regression, mostly because now there is an imbalance in the systems and the the CPUs are going idle, and the idle load balancer only kicks in at a later point in time to pull the task. And because of that disparity, we see that there is a bunch of regression reported by a bunch of workloads. All percentage differences are normalized. So if it's a lower value, that means there is a performance regression. If there's a higher value, that means there's an improvement. So looking at what exactly happens at update HDLB stats, right? Update HDLB stats at any given domain calls update SGLB stats, which goes over all the groups of the sched domain to compute the statistics for the CPU below them. But what update SGLB stats internally does is it does a for each CPU loop where uh, it does a for each CPU loop where it iterates over all the CPUs, and it computes the stats, looks at the stats, and then later discards it. If you move from a lower domain to a higher domain, you repeat this exercise where you again call SGLB stats on the groups there, and they'll again iterate over all the CPUs, even though nothing might have changed in the last time, since the last moment you had already done a load balance. So what we proposed is, yes, so instead, what we decided to try out was at SMT level, we calculate the stats for each individual CPU because that's the lowest level there is. And since thereon, we propagate the stats upwards. So MC no longer has to look at all the CPUs in the below it. It only has to look at all the SMT groups. So for a 8-core CCX, it reduces from 16 iterations to 8 iterations. For package level, which may contain 64 cores, now it is just 8 LLCs that it has to aggregate from. And that kind of reduces the time that update SGLB stats take. So the implementation looks like this, where each each sched group is actually derived from a sched domain struct itself, except for the sched groups of the lowest sched domain. Those are just the individual CPUs. And sched domain already has a SD shared object, which is shared among all the sched domains. So what we did was we have a SG shared object that points to the same SD shared object. So that way we now can send data from a sched domain to its sched group. And what we do in the SD shared is we embed this stats object that is used to aggregate the stats during load balancing. And whenever SGLB stats is called, we retrieve the stats for the sched group. And when we iterate across all the sched groups in a sched domain, we just aggregate all the statistics and update the shared object for the sched domain. So when we go one domain higher, the sched domain actually becomes the sched group. And that way we have the stats being passed seamlessly to the topmost domain. So we originally intended to use it for the busy load balancer. And the idea there was it is very periodic, and but just because it's very periodic and there are like a lot of CPUs doing it at the same time, we can at least get a idea whether things are working or not. And that is why this last update time we kept it as GFIS. Sorry, whoever told that we don't need GFIS anymore. Yeah. So we kept the time as GFIS, but we also wanted to see what the impact would be if we just reuse statistics very aggressively for all kinds of load balancing, for even newidle and idle load balancing. And what we saw was a mixed bag of results. There are a bunch of very active benchmarks that go in and out of idle that regress very badly. Also, the benchmarks that care about tail latencies. But what we saw was some of these benchmarks that really didn't care about load balancing, where just the wake up or the amount of activity in the benchmark itself would keep them in a balanced state. We saw that just reducing the number of cycles we spent in kernel actually improved the benchmark results a lot. And yeah, again, it's like a mixed bag of results. So we need to see what exactly is going bad. So a quick plug, my friends are developing this tool called per sched stats. What it does is it reads proc sched stats and dumps it in a human readable format. And then you can go back and compare the sched stats across two different kernel variants to see, okay, what has changed in case of preemption statistics, load balancing statistics. And some of the, and it's great for an early debug. So some of you did mention, okay, what is a great way to actually profile workload and present to the community that this is the behavior that the workload desires, and we are getting this from an alternate scheduler. What you can do is you can get this get start report to us, and we can take a diff and go see, okay, this particular statistics is changing, and then we can probably work that out into the EVDF file. Coming back to the presentation, what we did was we took this sched messaging 4-group case because it was constantly regressing and it just runs for 10 seconds. So that's a good enough time to measure, reiterate, and remeasure. And what we saw was the wait time has gone significantly up. So previously the task were, so for every time the CPU was busy, there was about 1.15% of the time a task was waiting. Now it has become 15% of the time. And in absolute numbers, it has become like 11 times. The wait time has increased by 11x. So we wanted to understand what exactly changed. And very interestingly, what we saw was if we do a very aggressive stats reusage, the number of attempts we are doing at load balancing goes up a lot. So at SMT domains, we are up 20 times. We are at MC domain, we are up 31 times. And at package domain, we are up 40 times. And we didn't really know why this was happening at this point. But what we knew was we are doing load balancing much more aggressively. That newidle balance, something the guard is tripping, and we are entering the new idle balance condition. And the guard trips for two reasons. One is that there is at least one CPU that has more than one tasks on it. And the other thing is the load balancing cost itself, which if it is more to go and search for a domain than the time the CPU was idle, we just bail out of the new idle balancing right then and there. So we went back and checked, okay, what are the stats on the tip compared to with these changes? What we saw was previously we would have bailed out 57,000 times at the very beginning, saying that, okay, it's just not worth it to do new idle balance. But now that number dropped by 18%. So we are tripping a guard that is going forward. And because of that, there is a cascading effect where each domain now is being traversed much many number of times. But then we also try to see what is the cost of doing new idle balance in this case. And what we saw was at the NSMT domain, it was like more or less the same because you don't really reuse stats here. You actually compute the stats from each individual CPUs. But every time you propagate stats, you see that there is a huge cost saving to be had. Basically, if you extend the concept of stats reuse for more than the periodic load balancing, you can get heavy cost savings. But the problem is there is no guarantee that whenever new idle balances are happening, the other CPUs might be doing new idle balance or not, because you can only reuse stats for yourself. You can't compute the stats for other groups that are beyond your control. And one more interesting thing that we found out was whenever we reuse stats, we found this number go up quite heavily, which is load balancer failed to find a busier queue on CPU newly idle. And what it really means is that you look at the stats, you say that, okay, this is my busiest group. By the time you converge on that group is no longer the busiest. You iterate over all the CPUs in that group only to find out that, okay, I can't pull tasks from any of these CPUs. Because this hackbench things are blocking very frequently, by the time you go and search for that busiest CPU, it's already gone. And those are the caveats that we found, is that it dramatically decreases the cost of new idle balance, because you don't need to go back and recompute stats for each and every CPU. You can just propagate it upwards. It's very likely cache hot. And you don't look at these data structures which can span across multiple per CPU. Because these are all per CPU data, it can also be on different NUMA nodes. So you don't iterate over CPUs, the CFS RQs and the RQ structs of the other CPUs. And the busiest stats may not be always, fresh in the whole Jiffy. Because we are still experimenting with Jiffy, we reuse the stats for the entire Jiffy. And the problem with rewriting stats very frequently, what we used was first sequence counter. And what we realized was, if you use a sequence counter, it is very likely that reader is just blocked on by multiple writers trying to update the stats, because they have just entered the new idle balance. They just saw a new state and they want to update the stats. And the readers get starved in that way. So, and we also want to do all of this locklessly on the reader side, because it's just too expensive to take a lock and look at the data. But you also want to see a consistent data.
Sorry, so yeah, did I get right that you said you have like a Jiffy worth of like status that you accept, and then beyond that you would
for this, yes.
Okay.
But in a later thing, we reduced it down to now it's 50 microseconds. So that is the amount of staleness we are okay with. And then now there is a little bit more of a cleanup mechanism that goes on. So basically the takeaway from this naive experiment where we don't invalidate anything is stats can go stale because the system is very busy and there are things going in and out of idle. But the busiest group, and that if you act on the stale data, it's even worse than not doing new idle balance at all, because now we are going and doing a bunch of things that really does not make sense anymore. So one more naive thing that we tried was this stats invalidation thing, where whenever CPU is going idle, we invalidate the stats of the local hierarchy. So we invalidate the stats for SMT, MC, and package domain where the CPU belongs. But the SMT stats for other cores are still, what to say, considered not stale. And whenever you pull the task from a busy source CPU, we invalidate the stats for its hierarchy. And this is something we tried out for new idle balance, because new idle balance happens so frequently that we need some form of uh, cache invalidation going on there. But again, what we found out was this again is like a mixed bag of result. The benchmarks that were previously benefiting are still benefiting to an extent, and the other benchmarks are still pretty terrible. And again, looking at sketch stats, what has happened is uh, we are ready from 11%, we are down to 9.27% of the waiting time. But that waiting time is still, what to say, pretty high. It's still 7x of what it is on the tip tree. So I, at this point, when we did when we froze the presentation, we really didn't have a good way to reuse the stats for new idle balancing. And but all the data pointed to the fact that okay, even with the stats invalidation, the new idle balance goes in because there is still at least one CPU that has more than one task, and because of that we have this cascading effect. But we still see some amount of cost saving at each domain, where the load balancing, whenever a load balancing is successful, we see that the time it took to succeed is actually less. So that is why we, what to say, in the end what we did was we only limited the stats propagation for load balancing, and then there is ongoing work to extend it to new idle balancing because that is still unreliable. But when doing this, what we also found out is that we, at some point we thought that okay, doing new idle balance for a long time is okay, but why is there no task waking up on this particular CPU? Okay. So what I also saw that so while doing this experiment, what we saw was there was a drastic difference in the wake up behavior, and we are doing new idle balance for a longer time. Why isn't this CPU being selected as an idle CPU for a wake up? And what we found out was that the idle CPU first checks for this context, which is whether the RQ cur is not equal to RQ idle. But in case of new idle balance, if we're spending a long time in new idle balancing, we're still doing it in the context of the previous task. The sched switch has still not happened, and the RQ curve still points to the previous task. And only later does it go and switch to the idle task. So one thing what we want to try is we set TTW pending for to notify that there is any pending wake up, even if it is not a remote wake up, and then get rid of this condition just to see what happens. That way, the CPUs that are still doing new idle balancing can be selected as a valid target to do a task wake up, because either their NR running is zero, or if they are in the process of uh, queuing a task, then TTW pending will be non-zero. So one of these conditions should trip and give us some result there. I mean, it should give an equivalent result of what an idle CPU is doing today. But that's something that is left to try out. And we limited the stats propagation to only periodic load balancing. And the pros are that from the cost saving, we saw that it does reduce time because now the stats are being reused at higher domain. But there is a con that to reuse stat at a higher domain, you have to align the load balancing intervals for all the domains. So if you want to reuse stats at a MC domain, you better hope that the SMT domain has done a load balancing just before you. So otherwise, you are going back and recomputing stats all over again. And what can happen there is because you are now aligning, say, 4 domains at once, the cost of doing a load balancing might be pretty expensive because the cost of 4 domains have added up. But we hope that with enough refinement, the benefits of the stats propagation will kind of mask this overhead where doing like 4 domains is still less costly than doing a whole one NUMA domain at the top. So that is where we want to get. And there's actually a V2 on top of this that tries to extend the stats reuse for newidle balance. So far, we haven't seen any improvement or any regression in benchmark. We have seen improvement in time it takes to converge on newidle balancing. So more testing, more feedback will always be helpful. Yeah.
So one thing that we might try is use Vincent's push queues, and on newidle simply iterate all the push queues and find a task and call it a day.
That was a speech to start thing.
Yeah.
Because pretty much you have like a bit mask of which CPUs have more than one task.
But in there, tasks are expensive.
Yeah.
Yeah, I mean, but Vincent is already tracking the migrated tasks.
Okay. Yeah.
I can definitely try that out.
It's basically what David has, but not shared.
Yeah. I can go back and take a look at the patch and extend that for newidle balancing.
Yeah, just linearly iterate the whole block, and as soon as you find the task, take it and say, I'm done.
Yeah. Thanks for the feedback.
Also,
Yeah.
with propagation of the hierarchy, of
Yeah.
the iteration hierarchy, we always move to the first CPU in the
Correct, yes.
At some point, I tried rotating that, and then I got it horribly wrong and moved on to other things. But it might make sense to try and revisit that, so that it's not always the first CPU in the mask that does the load balancing, because that's not really nice.
I'll revisit.
Whoever else is using that CPU, so we can rotate it.
Yeah, that is something on my to-do. So I'll go back and try that out where we rotate among the CPUs of the state domain and see how that fits.
Yeah, so except for the new idle balance, I think rest of the cases it's always the first CPU.
Yeah, I mean that's the simplest.
Yeah.
So if you start with every single CPU, then you do the SMT, so it's only the first of the SMTs, and when you go to the backend, it's only the first. So it's that first CPU that it's always penalized for having to do balance for whatever domain it's first of. And the larger the domains, the more pain it has. So if you can stagger that a bit.
For the busy load balance, yes. Now for idle load balance, so we say,
for busy.
yeah, busy.
For busy.
And so another thing, how do you ensure, because so if I remember correctly, we try to make sure that the load balance are not sync between CPU right now to prevent all the CPU accessing the same stat.
Correct. So this is again best effort because we never know what a particular CPU is doing. It may be in a interrupt disable state for a while, and that also staggers the whole thing a bit. So we hope that when we move to a higher domain, we have stats ready for at least some of our groups. The best thing to do would be to, as Peter mentioned, right, while rotating, we also find out which is the last CPU that will go to a higher domain and do load balancing and start from there. But that's something that I need to go back and relook. And that's something I am definitely going to try out.
But if you have a threshold that if you make a timestamp of when was the stats accumulated for a particular domain,
Correct.
and if you know that it does not cross a certain threshold, whatever threshold is for a particular domain, can you not reuse it in that case? Because staggering is going to happen one way or the other for reasons that you mentioned, right? Interrupts or software.
Correct. So even with our the version I have for the newidle balance, right? I see that the stats are being reused for about 50% of the time. The other 50% of the time, when it goes to check the groups, it does not find any valid stats.
You use the 50 microsecond?
The 50 microsecond is the limit.
But yet, you should have a look because I'm pretty sure that we are trying to make sure that the CPU will not update their statistics, will not do the load balance. No. Each domain are not always done at the same.
Yeah, correct. So I have
Sorry?
It scales by the size of the domain. So
No, but even we are not trying to do SMT, MC package NUMA at the same time.
Offset them by one.
We're trying to
Yeah,
offset to make sure that at the next tick we will go a bit higher.
Correct. So I have removed that condition and then added an additional logic so that this actually happens. So I do SMT now, and if I find that my next SMT load balancing interval is later than my next MC load balancing interval, I kind of pull it back. In some cases, it leads to more load balancing attempts because you're trying to pull it back. But maybe I can also try to push it a little bit front, and that should kind of work out. Those are something I'm going to go back and try.
I have a question.
Yep.
So I was wondering, like, you update the stats and then you do the load balance at a particular level.
Correct.
Then you pass the stats up.
Yes.
Right? Don't you have, like, aren't the stats stale now because...
So in case of busy load balancing, the busy load balancing only triggers if all the CPUs are busy and you select the first CPU from the CPU mask, as Peter mentioned. When you have everything busy, you are doing the sum of utilization load. So even number of idle CPUs is anyway 0. So if you move tasks below you, when you go to a higher domain, yeah, it won't matter because everything, you are just conserving everything within the group. And for new idle balance, you need a little bit of cleanup. So you can propagate it to a point where you have not pulled a task. But as soon as you pull the task, you say that, okay, whatever I have seen till now is stale because things have moved around and because it only happens for idle CPUs, right? Number of idle CPUs have changed now. And because of that, we invalidate all the stats and go forward.
Yeah, that makes sense.
And sorry.
Have you seen pathological cases where something explodes because the data is out?
Not yet, but I've also not run benchmarks looking for pathological cases. So it's mostly the very wake-up intensive benchmarks where I'm hoping that I don't see any regression, where it's not worse than what it is now. And yeah, but if there are pathological benchmarks, I'd love to know and give it a test.
It would be good to run one of these very long-running things where periodically you introduce an additional task where it sort of spoils the balance and see how long it takes to reconvert.
Well, those are the things I've not tried out. I've just tried out with a bunch of benchmarks that I generally test with. So any ideas there is also helpful. And yeah, so more experiments, right? When doing all of this, these are some of the experiments that I did, but I have not analyzed it to a great extent. One thing that Peter suggested on Chen Yu's newidle balance series was, hey, maybe we just need some task to be pulled during newidle balance as fast as possible. So we tried out this concept where we maintain a per LLC busiest CPU, which contains the most number of tasks at any given point in time. And the idea is anytime you do a NR running update, you just go compare yourself with the busiest CPU. And if you have more number of tasks than the busiest CPU, you just do a compare exchange. If it fails, it's okay because someone else has also turned into a busiest CPU and they would have set it. So it's not very expensive. And if you are the busiest CPU and you now have only single task, you just go and set -1 to this variable and just be done with it. Say that, okay, great. What we saw there was, again, a mixed bag of result. Some benchmarks are very happy with that, okay, we got a fast path to get this amount of work done as quickly as possible. Mostly the benchmarks which have run into this very overloaded case because of parallel wake-ups and sleep. But if you're looking at tail latencies or if you have some kind of a pinning involved, then we have seen that this does not really scale well. And the reason is multiple different CPUs going idle at the same time will look at the same busiest CPU, will try to grab its Runqueue lock, fall into a contention there. And going past that, it finds that it can no longer pull the task from that busiest CPU. So it might have as well not attempted this at all. This again was just an experiment we tried. And yeah, we have not really analyzed it to a great extent, but these are some of the contentions that we saw, and yeah, with that kind of primed us to know, okay, these are the things we should be careful about, the contention points which we should be aware of. And lastly, what we wanted to look at was sys node that Peter had proposed originally. So Tejan had come back, as Peter mentioned, he had come back with a problem where there was a small client CPU with multiple LLCs, but only a limited number of cores. And wake up would only explore one LLC, and it would only limit the wake up to 3 cores. And that was pretty bad. So what Peter proposed was, on top of the select idle CPU, what we do is, instead of just doubling down on one LLC, we just go and scan the entire node and see what happens. What we saw was, again, this leads to like a mixed bag of results. So it was later pulled out from the tip tree. But then we revisited to see what exactly is causing a problem here, right? And what we found out was 2 things. One is that there is no guard check for this particular loop that happens. So in a very busy system, if every wake up scans all the groups of your NUMA node only to find that there are no busy CPUs, that is just extra work for no good benefit. You could have might as well queued the task on some local CPU, get done with it, go on another wake up, and the load balancer would have kicked in to make the task, make the load equal. But now we are spending more time just to find an idle CPU. This task is not queued anywhere, so the load balancer can't see it. And because of this delay, and if you're waking up, say, 128 tasks, now that's like a pile up. So each search will take a longer time, and then there are 128 searches that will again go through this loop. Another problem that we found out was, we always start from first CPU. And because of sysutil, what happens is, there are only n number of CPUs you scan when you don't have an idle core. And if you don't have an idle core and you only scan, say, the first, all the searches will scan first 4 CPU of this particular LLC and say that we haven't found an idle CPU. And because of that, it's again wasted work. You go inside an LLC, only scan the first 4 CPUs. There might be idle CPUs right next to it, but you never end up exploring them. So there is no good way to actually solve this. I tried CPU mask distribute any. Problem is, the overhead of CPU mask distribute any itself shows up when you have a very wake up intensive task. Just looking at that extra per CPU variable, offsetting your CPU mask, that computation itself becomes very expensive. And in case of Hackbench, that's a 16-20% regression that I saw. So what we did try out was, okay, let's try to extend sysutil to one more level, where we would bail out from this select idle node very early on if we say that, okay, it's not worth scanning 2 LLCs either. And then for affinities, we did this one more check where we say that, okay, if the first mask of the LLC is not compatible, we just say that there is some pinning involved and it's not worth looking at it at all. That one LLC that we scanned is good enough. This ugly hack was required because in select idle CPU, the first thing we do is a CPU mask AND operation. And then we just look at these limits and we'll bail out without doing anything. And that extra CPU mask AND operation shows up. So we are actually baffled for a while that why this works. And then we realize that just because we are not doing one CPU mask AND operation, that becomes like 4% benchmark overhead for Hackbench. So with all these changes in place, again, it's a mixed bag of result. You see that at a lower utilization, benchmarks are happy. But as soon as you hit that overload threshold where you are just about to a point where your bailout thresholds are not being hit and you're going ahead on scans, but you very likely won't end up finding any idle CPUs. You hit into this large regressions here. And yeah, this again requires to be seen, like how do you solve it? One thing what we noted was that NR idle scan at a package domain is only updated once every 128 to 256 milliseconds. And that might be just too long of a time to gauge a system busyness. But we still haven't got to a point where we have a better metric to know how busy the entire socket gets and update it proactively to know this is the limit that we have to set and we have to bail out from here on. So yeah, that was my talk. If there are any questions, I'm happy to take them. So nothing hurt. So I'd like to thank my colleagues who have helped me with this, Gautam, Ravi, Swapnil, Dhananjay. And the per sketch tags has been an amazing tool for me. And it would be great if everyone can go and try them out for their various performance evaluation and let us know what is missing and if we can improve it in any way. And I would like to thank the folks sitting here for all their valuable feedback, review, and all the work you're doing. Thank you.
Thank you.